Let's now take a look at how we can implement Monte Carlo simulation. Um, First of all, what are the advantages or disadvantages of Monte Carlo simulation? Well, uh, for path-dependent options, it's great because for trees, if the path-dependent, you can have to, the branches will grow exponentially, but for Monte Carlo simulation, that would not be the case. So if you have path dependency, Monte Carlo simulation is the way to go. And also that the construction is actually not too difficult. You just need to simulate the path, and then you calculate your payoffs along the path and do your uh, discounting, calculate your um, value, and then you discount your value back all the way to time zero, and then just do an average at time zero. So it's relatively simple to implement and then to construct. And also that if you have multi-factor models, it's great because if you have multi-factor models, then you need to implement on the tree is really such a nightmare. It becomes so complicated very quickly and becomes really unmanageable. But for Monte Carlo simulation, it's really not a big deal. So if you have the different factors, as long as you have the covariance matrix, that you know how when the shocks are linked together, um, you can, or you can basically draw the shocks from a joint distribution, then you can handle a multi-factor model relatively easily. The main drawback really for Monte Carlo simulation is that it has some difficulties in pricing American style options. It's not that you cannot, because of the advantages that enjoyed by Monte Carlo simulation, people do try to price American style options through Monte Carlo simulation as well. There's been many attempts to do that. The challenge here, obviously, is to figure out the region where early exercise is going to be taking place. So if you know the region, then once you simulate your path, and if as long as the point along the path is in that region, you would then exercise. So that path will get cut off because you then at that point you have exercised the option or exercised the financial derivatives. Um, and if the path does not go across the exercise region, you can just continue that path so that you will not exercise, the path will continue. But it's quite tricky to estimate the exercise region, and and that region is very dependent on the nature of the derivative asset itself. So sometimes it can be very tricky. But in general, if it's not American styled option, Monte Carlo is actually a good way to go. Now, what is the step to calculate your options or the price of the financial derivatives using Monte Carlo? So first, you need to generate distribution. And obviously, initially just gonna generate, out of a uniform distribution there, right? And then you wanna convert this random draw into a distribution, that is of your desired distribution. So if you use normal distribution, what you're drawing here out of the uniform distribution then is your the number of standard deviations that you have drawn. So what do I mean really by that? Okay, let's take a look at the a normal distribution table there. Just suppose we want to draw distribution out of a standard normal distribution. So what do I do? So here I have the cumulative standard normal distribution here. So suppose you out of the uniform distribution, you basically are drawing numbers from 0 to 1, strictly greater than 0 and strictly less than 1. Now, suppose you have drawn a number which is 0.9772, then you know that you are 2 standard deviation away from mean. So then you will get the number of 2 standard deviation. If you draw a number that is 0.5398, is 0.1 standard deviation. Also, if you draw, say, a number that is 0.1788, you know that you are 0.092 standard deviation away from the mean. So here you're on the left. Then those numbers that we have, either say 2 standard deviation away, for example, and then you just multiply by volatility. So then you get your random shock, right? So once you have got your random shock for independent ones, because we have done independent draws, initially the draws are uncorrelated. Then we go through a correlation process to make them correlated. So this is the needed when you have multi-factor model and they are, those random shocks are correlated. Then you need to go through that process. Okay. So you get the correlated shocks, and then so you're just gonna simulate discretized random process. So you're at a point here, you're just gonna simulate your paths, and each point along the way is determined by the drift, which is the expected change, and plus a random part, which is unexpected, or the random change that is based on what we have built earlier in the first 3 steps. Then you basically then build a path for the underlying asset at maturity, for example, or along the time from current all the way to maturity. And then you, based on each path, you can calculate what the derivative asset payoff will be. And so you generate n number of such paths, then you get n number of such payoffs. So along each path, you can discount that payoff back to the current time. And then you get n number of such discounted value payoffs, or discounted value or discounted payoff, then just take an expectation, or just take an average of that. You will get the value or the price of the derivative asset. Now, because you're generating the path based on the distribution that you have created, then this average is the average based on the probability measures that you have created. And if in your path the all asset is actually growing at the risk-free rate, then you basically have generated distribution that are under risk neutral. Okay, so in risk neutral and in the real world probability, the volatility is they're still the same. The difference is really with the drift or the expected growth rate. And if you use growth rate being the risk-free rate for all the assets, then you are generating under the risk-neutral probability measure. And then you can, basically, that's why you can do this straight average to calculate your price of the derivative asset. So this basically shows how we can generate correlated random shocks based on or starting from uncorrelated random draws that we had. So you had an X here, you get an E1, and you have two random shocks, X1 and X2. They are uncorrelated, but you get this alpha 2-1 and alpha 2-2. Alpha 2-1 is calculated based on the correlation between factor 2 and factor 1. Then alpha 2-2 is really that alpha 2-1 square plus alpha 2-2 square. Okay, so just for this Cholesky decomposition approach, you can basically then calculate a whole bunch of E1, epsilon 1, epsilon 2. And this is supposed to be epsilon 3. And so from X1, X2, and X3, which are uncorrelated, but epsilon 1, epsilon 2, and epsilon 3 are correlated. Now I have just changed this to epsilon 3. Now we can generate the correlated random shocks from uncorrelated shocks through the approach of, Cholesky decomposition, where we can decompose a covariance matrix and then which will give us the alphas that we need to change uncorrelated shocks into correlated shocks. Now, Cholesky decomposition has some, I should say, limitations because number one is computationally intensive. So it has to decompose a matrix. Basically, you're going to decompose a covariance matrix. It's quite computationally intensive. And so if the matrix is really large, it will take a long time to decompose that. And typically, you may have several hundred stocks and their movement are all correlated. So for example, you have S&P 500, you have 500 stocks, they're all correlated. So then you are looking at decomposing a matrix that is 500 by 500, which is very big, and it'll take a very, very, very long time to decompose that. And in those cases, it's probably not feasible to do. The other drawback for Cholesky decomposition is that it requires the matrix to be positive semi-definite. Now, in reality, all covariance matrices are positive semi-definite. So if everything is right, and it should be okay. There's not a problem here. It's not a restriction. However, when you measure the covariance matrix, there's always some numerical error there. So in reality, although the actual covariance matrix may be positive semi-definite, when you calculate the correlations and covariance and actually because of the imprecisions you have, the matrix that you end up may not necessarily be positive semi-definite, and that will create an issue for Cholesky decomposition. So typically if we have large number of correlated assets that we need to simulate, so instead of going through Cholesky decomposition to generate correlated random shocks, we typically will use an approach where we will have a market movement, and then a bunch of each of the individual components of that has two components and move. One is the market move, the other one is their independent movement. So if we have let's say take S&P 500, for example, if you simulate the correlated movements of each individual stocks within that portfolio of S&P 500, you're not gonna go through a Cholesky decomposition to generate correlated movements. Instead, you're gonna generate one factor that is a market movement, and the individual stock movement will have a sensitivity to the market movement plus a scaling factor times their individual shocks, and the shocks between the market and their idiosyncratic movement are not correlated. And in this case, for a S&P 500 portfolio, you let's say if we have a single factor for the market and a single factor for each of the idiosyncratic shocks for each stock, then altogether you have 501 shocks you need to produce, and all of them are actually uncorrelated, and then the correlation among the stocks are really through their sensitivity with this common market movement that generates the correlation across the different stocks. So doing Monte Carlo simulation to estimate, well, you will get a number. This number obviously is an approximation, and you will get more precise approximation if your number of paths becomes more and more. So the larger the number of paths you generate, the more precise of your estimate will be with the true value. Now, Monte Carlo simulation is actually an unbiased estimator. So when you take the actual average within the sample, you have a sample average, but what you really need is the population average. So but as the number of runs or the paths becomes bigger and bigger, your sample mean will actually converge to the population mean, and in an unbiased fashion, okay? And you can actually estimate the you can actually generate a confidence interval for your estimate based on the number of paths you have and the standard deviation of other correlations, the volatilities of the process. Okay, so and which is nice because you know how much confidence you have with the estimate. So you will see the range of that confidence interval that gives you a sense of how much you can be off, and then you obviously can and this also tells you how many additional path you need to generate in order for you to reach to a pre-designed confidence interval. Now, in generating the random numbers, there's a technique where you can actually put a seed there. The use of that seed is you can actually generate repeatable paths. So when you really draw a random number from the computer, it's actually not quote unquote really random. It's actually a based on a deterministic path, but the numbers that's coming out of it generates a particular distribution. So you can have a uniform distribution out of that by looking at the numbers you generate out of that random number generator. But in reality, they just taking it's really a deterministic routine. I should say that if you know the starting point, then the process is actually deterministic. So that sequence depends on the starting value. And if you always choose the same starting value, you can actually have a set of repeatable random numbers that's generated for you. So every time the path will be exactly the same. So sometimes in risk management, it's actually useful that you can put in a seed then and put in the same seed every time that you generate exactly the same path, because then you know the change of value is not due to the inherent randomness that you have from the simulation, because the paths are repeatable paths. Because you are putting the same seed there. There are a lot of details related to handling the numerical aspect of Monte Carlo simulation. There are some random number generator better than the others. So we're not going to go into those kind of details in this particular course, but those are the things where you should take care of or be mindful if you are the ones that really needed to have high precision in calculating your derivative price. So a lot of the quants will actually need to worry about what numerical routines you actually use to generate that random number generator. If you use Excel is probably not it does have one, but that random number generator is probably not the best for a number of various reasons that I'm not gonna go into. But as a a toy model or something, or you do a quick and dirty construction of a model, you can still use that. It's easy to implement, so you can implement it in Excel VBA and will quickly get your results. But just to be mindful that that random number generator is probably not the best ones, and you should really use if you want to do some serious stuff. Now, there are a number of techniques people usually throw to Monte Carlo simulation just to make sure we get better efficiencies from the simulation. Now, we're gonna talk about a few in this course.